You ask me a very interesting question. You ask if an ordinary person, just a regular guy off the street, by studying hard, would get to be able to imagine these things the way I imagine them. And my answer is a resounding yes, of course. Because you have to understand, I was an ordinary person who just happened to study hard. There are no miracle people. There's no special physicist breed born with a quantum mechanics lobe in their brain. It just happens that they got interested in this stuff. They got fascinated by the puzzles. And they learned all this stuff. But it's work, you see. There is no talent, no special miracle ability to understand quantum mechanics or a miracle ability to imagine electromagnetic fields that comes without practicing and reading and learning and studying. So if you say, take an ordinary person who is willing to devote a great deal of time and study and work and thinking and mathematics and messing around with the ideas, then he has become a scientist. It's a transformation through effort, not birthright. Now, when I'm actually doing my own thing, when I'm sitting there working in this high, deep, and esoteric stuff that I worry about, people always want to know what it feels like. What's the picture in the mind? And I don't think I can describe it very well. It's a messy business. First of all, it's like asking a centipede which leg comes after which. As soon as he thinks about it, he falls over because it happens quickly. And I'm not exactly sure what flashes and stuff go in the head. But I know it's a crazy mixture, a jumble of partial equations, partial solving in equations, scribbles in the air, then having some sort of vague picture of what is happening that the equation is saying is happening. But they are not that well separated as the words I'm using now. It's a kind of a nutty thing, a dynamic mess. It's very hard to describe, and I don't know that it does any good to describe it because it's so personal. And that brings me to something that struck me recently. Something very curious, which is that I suspect that what goes on in every man's head might be very, very different. The actual imagery or semi-imagery which comes up when we think. When we are talking to each other at these high and complicated levels, physics or math, and we think we are speaking very well, we nod and say, yes, yes, thinking we are communicating perfectly. But what we are really doing is having some kind of big translation scheme going on for translating what this fellow says into our own private images, which are very different from his. I found that out in a funny way because in the very lowest level, just the most basic thinking, I wouldn't go into much details, but I got interested in our sense of time. I was doing some experiments, just fiddling around, really trying to figure out something about our time sense. And so what I would do is try to count to a minute. Actually say I'd count to 48, then it would be 1 minute. So I calibrate myself like a clock, and I would count a minute in 48, thinking I was counting seconds, but it turns out I'm a bit fast, but it's close enough. And then it turns out, if you repeat that you can do it very accurately, when you get to 48 or 47 or 49, not far off. You click a stopwatch, and you're very close to a minute. And I was trying to find out what affected that time sense. Does it change if I'm hot, if I'm tired? And whether I could do anything at the same time I was counting. And I found that I could do many things. I could run up and down stairs. I could do physical stuff. But there were some things that just stopped me cold. For example, I had great difficulty. I was in the university, getting my laundry ready, and I was putting the socks out, and I had to make a list. How many socks? And there were something like 6 or 8 socks. And I absolutely couldn't count them because the counting machine in my head was being used to count the time. I couldn't count the socks until I found a trick. I found that I could put them in a pattern and recognize the geometric shape of the number. And so I learned a way after practicing by which I could count the lines of type in a newspaper and see them in groups. 3, 3, 1, that's a group of 10, 3, 3, 1. Without saying the numbers in my head, just seeing the groupings. I could therefore count the line of types, practicing with the newspaper. At the very same time, I was counting internally the seconds for the minute experiment. So I could do this fantastic trick of saying 48. That's 1 minute. And there are 67 lines of type. You see, it was quite wonderful, like a circus trick. And I discovered many things I could read while I was counting. I could read perfectly, all right, and get an idea of what the article was about. But I couldn't speak, I couldn't say a word. Because, of course, when I count aloud to myself inside. I say 1, 2, 3. Sort of with an inner voice in the head. Then I went down to breakfast, feeling very proud of myself. And there was John Tukey, a brilliant mathematician at Princeton at the same time. And we had many discussions, and I was telling him about these experiments and what I could do, and he looks at me and says, "That's absurd." He says, "I don't see why you have any difficulty talking whatsoever. And I can't possibly believe that you could read. Reading is impossible while counting." So I couldn't believe his attitude. but we calibrated him. It was 52 counts for him to get to 60 seconds, or whatever. I don't remember the numbers now. And then he said, "Oh, what do you want me to say? Mary had a little lamb. I can speak about anything. Blah, blah, blah. Blah, blah, 52. That's 1 minute." And he was right. He could talk a blue streak while counting time. And I couldn't possibly do that. And then he wanted me to read because he couldn't possibly believe I could do that. So we compared notes, digging into what was actually happening. And it turned out that when he thought of counting, what he did inside his head was entirely different. He saw a tape with numbers ticking by. It went clink, clink, clink. The tape would change with numbers printed on it. He could see it. Well, since it's sort of an optical system that he was using, and not a voice system, he could speak as much as he wanted. His voice center was free, but if he had to read, well, that uses the optical system. So then, he couldn't look at his clock. Whereas for me, it was the other way around. I use my inner voice. And that's where I discovered, at least in this very simple operation of counting, the great, vast difference in what goes on in the head when people think they are doing the exact same thing. And so it struck me, therefore, if that is already true at the most elementary level, counting socks and seconds, that when we learn mathematics and Bessel functions and the exponential and the electric field and all these high-powered things, that the imageries and the method by which we are storing it all and the way we think about it could be really, if we could get inside each other's heads, entirely different. And in fact, this explains a lot. While somebody sometimes has a great deal of difficulty to understanding a point which you see as obvious and vice versa, it's maybe because it's a little hard to translate what you just said into his particular framework. His mental machinery just doesn't run on that kind of fuel, and so on. Now I'm talking like a psychologist, and you know I know nothing about this. I'm just a guy observing his own head. But suppose that little things, atomic things, behaved very differently than anything that was big, anything that you're familiar with. Because you see, as the animal evolves, and so on, as the brain evolves, it gets used to handling ordinary circumstances. The brain is designed to avoid being eaten by a tiger, to throw a rock, to understand things on the scale of inches and feet. But if the gut particles, the deep inner workings of the universe, work by some other rules and some other characters, if they behave differently, very differently than anything on a large scale, then there would be some kind of difficulty in understanding and imagining reality, wouldn't there? And that difficulty, my friends, is exactly where we are. The behavior of things on the small scale is so fantastic. It is so wonderfully, marvelously different. It is so different that AMYTHING, that behaves on a large scale, is a bad analogy. You say, electrons act like a wave. No, they don't exactly. They act like particles, like bullets. No, they don't exactly. They act like a kind of a fog around the nucleus. No, they don't exactly. And if you want to get a clear, sharp picture of an atom so that you can tell exactly how it's going to behave correctly and have a good image. In other words, a really good image of reality, I don't know how to do it. Because that image ultimately has to be mathematical. We have a mathematical expression, a strange mathematics. I don't understand why it is that way, but we can write mathematical expressions and calculate what the thing is going to do without actually being able to picture it. It would be something like a computer in which you put certain numbers in and you have a formula for what time the car will arrive at different destinations, and the thing does the arithmetic to figure out what time the car arrives, but the computer cannot picture the car. It is just doing the arithmetic. So we know how to do the arithmetic, but we cannot picture the car. It's not a 100% failure, because for certain approximate situations, certain kind of approximate pictures work. Thinking of it as a fog works for some things. Thinking of it as a wave works for others. So when you're working with certain particular aspects of the behavior of atoms, for instance, when I was talking about temperature and so forth, thinking that it's just little balls bouncing around is good enough, and it gives a very nice picture of temperature. But if you ask a more specific question, and you get down to deep questions like, how is that when you cool helium down even to absolute zero, where there is not supposed to be any motion, it becomes a perfect fluid, and it has no resistance, and it flows perfectly, and it isn't freezing. Well, if you want to get a picture of atoms that has all of that in it, I can't do it. But I can explain why the helium behaves as it does by taking my equations and seeing that the consequences of them is that the helium would behave as it is observed to behave. So we know that we have the theory, right? But we haven't got the pictures that would go with the theory. And is that because we haven't caught on to the right picture yet? Or is it because there aren't any right pictures for people who have to make pictures out of things that are familiar to them? Well, let's suppose it's the last one that there's no right picture in terms of things that are familiar to our daily experience. Is it possible then to develop a new familiarity, to get comfortable with those things that are not familiar on hand? By studying, by learning the properties of atoms and quantum mechanics, by fiddling with the equations until it becomes a kind of second nature. Just like it's a second nature to know that if two balls come towards each other, they smash into bits. The two balls, when they come toward each other, turn blue. You know what they do. So, the question is whether you can get to know what things do without picturing them better than we do today. As the generations develop, will they invent ways of teaching so that the new people, the kids coming up, will learn tricky ways in looking at things and be so trained, so well trained, that they won't have our troubles, they won't have this picturing problem with the atom. There's still a school of thought that cannot believe that the atomic behavior is so different than large-scale behavior. They just refuse to accept it. I think that's a deep prejudice. It's a prejudice of being so used to large-scale behaviors, and they're always seeking to find, always waiting for the day that we discover underneath the quantum mechanics there's some mundane, ordinary balls hitting or particles moving and so on, just like in the playground. But I think they're going to be defeated. I think nature's imagination is so much greater than man's. She's never going to let us relax. She's always guarding one more secret that's stranger than the last.